Okay, well, thanks, Shiab, for the kind introduction, and thanks, Malcolm, and the whole organizing committee for this invitation. It's truly a pleasure to get to present our work in such a distinguished crowd. Um, Please catch me if I'm going over time. I think I prepared a little bit too many slides, so yeah, but don't hesitate to. We'll just skip some slides if need be. Before I start, I wanted to make sure that I was spending some time on the most important slides. So the work that I'll be presenting to you today is actually the result of a wonderful team that I have the chance to work with at Meta and in academia. In Paris, we have a PhD program which can be done in between industry and universities, which allow this. And without all of these people, of course, the work would not be possible. So it's really their work rather than mine. Okay, given the crowd, I don't think it's really useful to insist how remarkable our species is. We have somehow acquired an ability for language we can communicate extremely complex thoughts by articulating them either through our vocal track or even through sign languages. And this provides us with an incredible ability to accumulate knowledge and techniques, which is really the basis of our civilization. And of course, the big questions behind this ability is the neural system or the biological system that allows this feat. It seems to be unique in that no other species have the ability to understand or combine new words into new meanings, and it's unique. Or at least it used to be unique until recently, because for the first time now we have models, AI models, that seem to also be able to process language to some extent. And the goal of this talk is not so much to convince you that they are indeed processing language exactly like we do, but rather to highlight how we can use these large language models to try to decipher and better understand how the brain may learn to present language and may be able to combine words together to produce meaning. All right, it's the classic recipe that the community has been following, and we contributing in this direction too, is kind of a naive comparison between the activations of deep neural networks to the activations of the brain. So a classic setup is you take a deep net, which has been pre-trained for, let's say, speech processing, completely irrespective of neuroscience. And you want to see whether the activation that the deep net generates in response to some speech sounds are in any way similar to the activations of the brain in response to the same sounds. So for instance, you can use functional magnetic resonance imaging. This is in this case, a study that was led by Juliette Millet, which I already showed last year, but it will just be used as an introduction. I'll go very quickly on it. Juliette Millet and Charlotte Cocheteux, who curated a lot of public data sets to work with a bit more than 400 individuals who were listening to natural stories in the fMRI scanner. So they listened to stories like The Little Prince, which was acquired in Eurospin in the south of Paris. They also listened to podcasts and or isolated sentences. And for each of those, let's say, sentences, we can try to get an activation pattern, which we can compare to a deep net. And in this case, we focused on a deep net called Wave2Vec 2.0. It used to be a state-of-the-art deep net model for speech processing, typically used for automatic transcription or for source separation. I won't go into the detail of this deep net, but the main objective of this deep net is interesting. It's self-supervised. It tries to predict its own activation. So it does not need anything but the audio track for it to learn to represent speech, apparently. So what you can do is try to see, in response to the same sound, does Wave2Vec2 activate in a similar way to the human brain recorded with fMRI. Now that's a non-trivial comparison because you don't know what to compare exactly. You have many neurons in the deep net, you have many voxels in the brain. So the classic method to do this comparison is a so-called encoding or linear regression method. you can fit just a linear regression to try to predict brain activity given the activations of your model. And if you can, then that means that you have a linear mapping between these two systems in response to the same sound. And so this linear mapping would suggest that they would represent information in a similar way. Let me show you a cherry-picked example. On the horizontal axis here is the time from the beginning of a story at T0. And on the vertical axis is the amplitude of the bold response in one voxel. And the black line is the actual measurement of the bold activity. And the red line is this linear readout of Wave2Vec 2.0, linear readout optimized to predict that particular voxel on a train set. And you can see that the bold activations tend to be similar to the readout activations of Wave2Vec 2. It's not completely identical, but if you were to correlate the black line and the red line, you would have a decent correlation value. But in response to the same input, it has the same activation. So that's a good sign for computing the same function. Okay, so that's for one voxel, cherry-picked actually in the superior temporal gyrus over here. You can repeat this operation for every individual voxel in the brain and have a method to systematically compare the activations of the brain to the activations of the deep net. Now, in a sense, this is not that interesting. What is interesting is really to do this for each layer of Wave2Vec 2.0. So you can repeat this operation, try to see whether there is a linear readout from the first layer to each voxels. And then you do the same operation for the second layer to each voxel, for the third layer to each voxel. And what you see here is the result of which layer. It's a result that indicates which layer would be best at predicting brain activations. And what do we see? We see that in the early auditory areas, the activations of the brain seems to be most linearly predictable from the early layers of the transformer. Whereas in higher level regions, like in the anterior temporal lobe, in the inferofrontal gyrus, the voxels are color-coded in red. And this means that their activations in response to speech tend to be best linearly predicted from the deepest layers of the deep net. And you have this kind of remarkably homogeneous gradient in between these two extremes, in between the auditory cortex and the high-level regions like anterior temporal lobe or prefrontal cortex. And this to me was a striking result because that means that you can train an algorithm designed for industry, right? For automatic transcription, source separation, things that have direct applications in the industry. Train this algorithm and with a self-supervised learning objective, so just with audio data. And yet this algorithm will apparently, after training, learn a hierarchy of speech representations which linearly maps onto the known hierarchy of speech processing in the brain, even evidencing hierarchy that we suspected but we did not know about. For instance, starting from the motor and premotor areas, probably coming from the larynx region over here and climbing up to the prefrontal cortex. That's striking. We have an AI model not designed for neuroscience, which seem to be at least partially similar to the human brain during speech processing. So the whole goal from this result is to try to see whether we can now unpack these brain responses and try to decipher the underlying mechanism, and that will be the objective of this talk. All right, so what I just showed you is an example study where we compare these AI models to the adult human brain. This is the most classic approach. What I'll show you is that we can also do this in the developing brain, in the brain of children. And this is very important because we have models that can be trained, so they also develop over time and over language exposure. And we can compare this development of language in the model to the development of language in the human brain to some extent. Right. So the underlying motivation originally was to try to understand exactly the developmental trajectory of language in the brain, because this is remarkably efficient, right? So young children can learn language with a very small amount of exposure. So the typical average amount of word that we hear every day is around 10 to 13,000. So that means that in a few years, you'll be just exposed to a few million words, and that apparently suffices for children to acquire most of language, not all of the world knowledge, but the rules that suffice for understanding new sentences, and to some extent, a large part of the lexicon that they will use for the rest of their lives. And this is in sharp contrast with large language models, which at the time where I designed these slides, were trained with billions of words, but it's now several orders of magnitudes higher. The current large language models are trained with trillions of words, and they are very impressive, but in a sense, they're also impressively inefficient at acquiring language. But understanding how the human brain reached this level of efficiency and develops itself for language processing is remarkably hard to study, because we don't have access to children brain responses in general. It's already difficult to study adults in the fMRI scanner. And it's very, of course, extremely difficult to study younger children, especially in the age of 2 to 5, because they really start to move and not really comfortable in staying still for more than a few minutes in the scanner. And some people did obviously try this, and with remarkable result, but it's still technically an extreme challenge. And I was sort of complaining about this to one of my friends, Pierre Bourdillon, who is a neurosurgeon. He was saying that actually they have access to pediatric recordings on a weekly basis, because they are operating on young children who suffer from epilepsy routinely. And this potentially could offer a window on these brain responses to speech. So we hired a bright PhD student who now graduated, is a postdoc in the team, Linnea Evanson, to try to see whether we could apply the same tool that I just showed you in the context of fMRI and adult speech processing, but this time in the context of intracranial recordings in children suffering from epilepsy. And this is a heavily clinical setup, right? These are young children who suffer from drug-resistant epileptic seizures. The goal generally for the clinical team is to perform surgery as young as possible, with a pretty strong barrier around 2, because before 2-year-old, the skull is not sufficiently rigid, and so there is a risk that the stereotactic electrodes that are implanted inside the brain would move. And so they try to really identify and remove the pathological brain tissues from the brain as young as possible. The bottom line is that these children come to the OR, let's say on Tuesday or Wednesday. They get surgery, and then they wait for about a week in the clinics until they have a sufficient amount of epileptic seizures, so that's the epileptologist and the neurologist can be confident about the brain region which is causing the epileptic seizures, and should be removed if it does not prevent a major cognitive or motor function. So what Linnea did is to ask the legal guardians, the parents generally, and the children, whether during that week of waiting in the clinics, whether they would be happy to listen to natural stories. So she made a little app on a phone that she lended to the participants, and they could just play a chapter of The Little Prince every time they wanted. And then we can time lock the brain responses of every individual phonemes, every individual words in each of these recordings for each patient. We recorded over the past 4 years, 46 patients who are aged from 2-year-olds and up to adulthood, which gives us a pretty large coverage of the cortex and some subcortical areas, perhaps at the exception of the occipital lobe, where epileptic seizures tend not to occur. And I should stress here, I'm sure you all know this, but to stress this, as of course the electrode implantation is done completely independently of the research, so we cannot bias the decisions of where to put the electrode. This is solely decided by the epileptologist and the neurological team to try to target the most likely areas causing the seizures. All right, so we divided the analysis into three groups, mainly for simplicity purposes. So we have a young cohort of 2 to 5 year olds. These are 10 patients, 16 patients aged from 6 to 11, and of course, I'm blocking my screen, 20 patients above 12 year olds. For each of those, we have slightly different coverage, but generally speaking, we have a good coverage of the brain. On average, the brain responses to speech seems to be similar. So, for instance, this is a proxy for the power response across electrodes, time log to the word onset, and there doesn't seem to be clear differences across age group. Now, if we use an encoding model, like I showed you before, just this linear regression, there is it's a temporal kernel adapted to it, which I occluded, but some of you may know this as a temporal receptive field or finite impulse response function. When we try to predict brain activity based on some linguistic features, phonetic and lexical features that I'll show you in a second, we can model or we can predict how the brain should respond depending on natural speech. And then we can evaluate how well these predictions are as compared to a ground truth on a held out test set. And overall, what we see is that we can better predict the brain in the older participants than in the younger cohort, as you can see here. Especially this difference is true in the language network, so in the superior temporal gyrus, superior temporal sulcus, but also in areas which are nearby Broca areas, so the lateral and infrafrontal cortex here in orange. The feature that we focused on are the classic linguistic features. So for low-level features, we focused on phonetic features, like whether a given phoneme is a vowel or not, whether it's plosive, whether it's voiced or not. And for each of those, we can try to see where and when this feature can be identified in brain activity. So for instance, here on this diagram, you have a time course on the horizontal axis. T0 is the onset of a phoneme, and the vertical axis tells you the correlation between the true brain activity and the decoded activity for each of those features, which would be each of the lines. That's one way to look at the data of time. Over time, you can also do this similar type of analysis of a space for each electrode and see that it tends to peak in the expected areas of speech processing, in the superior temporal gyrus in particular. But this rich set of features that seem to be decodable for each age group relatively similarly. At least we don't see a statistical difference across age groups. Now, if we focus on high-level features, lexical features that describes whether words are nouns or verbs, whether they are frequent in natural language or not, we see a slightly different time course. We see that these features are much longer lasting, over 2 seconds on average. And they are slightly more distributed. This more distributed if we really focus on what's remaining once we remove the low-level features. And importantly, the other thing that we observe is that this set of high-level features seem to develop over time, or at least over ages, I should say. They are present in the youngest cohort, but not as well as in the older children. So 6 and above year old participants tend to have better representations of these lexical features. Okay, but this is a summary of what I just said. In time and overall in the brain, we see that these phonetic features tend to be represented across relatively similarly across age groups, whereas we tend to have a difference for the lexical features across ages. And we can explore for which region this seems to be the case, and this age difference seems to be particularly present in the high-level areas, like in the lateral and frontal cortex.
Jean-Remi?
Yes.
The 2 slides back, how do you, yeah, there. where did you come up with this sequence of adverb, adjectives, and so on? Why should that be in that order? Why is it?
Sorry. Yeah, this is just for clarity. It's color coded by how well the representations can be decoded. So the adverbs are the lowest on average. They are the hardest to decode, whereas the pronouns on average are the easiest to decode. So it's not a priori, it's a posteriori color coding.
Oh, I see. So this is what the finding is.
Yeah, exactly.
And does that match any linguistic logic to it? Why should verbs be so bad compared to nouns?
I don't know. I think we would need to ask a linguist and a developmental psychologist and a linguist. Yeah, to me, this disordering is not obvious. That's just it's just an observation. But maybe some people can relate this to other findings.
Hey, Jean-Remi, this is Sherry.
Yep.
I have a question also about this. This is a linear decoding analysis.
Yes. So the time course here is decoding over time, and the brain plot is an encoding.
Okay. Got it. So I guess then how much of this relates to the actual behavior in terms of how much the kids and the adults, how much kids in different age groups understand different phonemic categories or word categories? Because an alternative explanation could be that this information is not linearly accessible, but is still present in the system or is represented differently across age.
Yeah, absolutely. I think this is actually what we're trying to understand, right? Is why don't the young kids understand? It's because they don't form these representations. So there's kind of a chicken and egg problem in here. But yes, we don't know. We don't have like for each sentence a comprehension question. But presumably, when you are 5-year-old and you're listening to The Little Prince, it's much harder to understand the whole story, the whole narrative. Perhaps there are many words that remain opaque as compared to if you're an adult and you listen to the same story. So I think there is a link, but we don't demonstrate it in this study. Yeah.
Got it. Thank you.
Okay.
Sorry, is there another question?
No, go ahead.
Okay. All right. So this were an analysis with classic interpretable linguistic features. We can do the same type of analysis with AI features. So by looking at AI activations like Wave2Vec 2.0 that I showed you before, try to see whether the different layers of Wave2Vec 2.0 indeed linearly predict brain activations in response to speech. So we here, for sake of simplicity, focus on three conditions. Either an early layer in the algorithm.
Before you start, there is some questions in the chat about this previous section. One is about training. Is the target the area in the brain? If so, why unsupervised?
I'm sorry. I don't think I understood the question. Can you repeat it?
So I guess I'm going to try to interpret it. I assume the question is asking if the target that you're training the model on is to match an area in the brain, why are you using unsupervised training for the models?
Okay. All right. I think I understand the confusion. So I should stress. I'm not going. It's true that I'm going very quickly on the methodological details. There are really two things to separate. There is, on the one hand, the features, which can be linguistic features or AI models. These are sort of models in a sense of cognition. And they, in the case of Wave2Vec 2, it's unsupervised in a sense that it's trained to predict, or it's trained on an objective, which is to try to represent speech data, but it's trained completely independently of the brain. In fact, in this study and in many other studies, we don't even train this Wave2Vec 2 model ourselves. We just download it from Hugging Face. And then there is another part, which is the linear mapping. So when we want to compare some cognitive features let's say, linguistic features or Wave2Vec 2.0 activations, when we want to compare these features to the brain, we have a little training procedure, which is this linear regression. And so these are really different type of thing. The latter is made to evaluate the similarity between the features and the brain, where the former is made as a model of representations in vectorial systems. But I hope this is clear. The interesting aspect for Wave2Vec 2 is that it's not supervised, so you don't train Wave2Vec 2 with text, and that to me is really interesting from a developmental trajectory, from a developmental perspective, because we as humans are not trained to understand speech by getting a lot of, let's say, text annotations. We just learn speech presumably from context, but really without any supervision, or most of the time without supervision. And so ultimately focusing on models that are not supervised is probably the way to go if we want to understand how the brain acquires language. But these were different points. I hope you answered the question.
Yeah, there's another question that says, yes, so there was a follow-up from Oded that was clarifying his concern. So there's a separate question that said, I wonder if the difference between low and high levels would be less in case-based languages where word ending, i.e. a few phonemes, indicate grammatical function more routinely.
I think that's a possibility. I don't think we have addressed this question in the paper. So yeah, if you have a hypothesis, more precise hypothesis to test, that would be great to make those suggestions. I would be happy to look into this. Yeah. Or whether I would be happy to ask Linnea to look into this. It's slightly different. All right. Okay, I'm gonna rush a bit. So so if we do the comparison now between not linguistic features, but between the AI features, the features that are being learned by AI models like Wave2Vec 2, we focus on two layers, an early layer and a deep layer for the sake of simplicity. And we also compare this to an early layer when the model is not trained, just to see what the chance level is, because there is a lot of things that any model, even a model that has not been trained on anything, could capture in brain activity. For instance, volume is something that a random model would be able to capture very easily. And so for each electrode and each individuals, we can try to learn the mapping between Wave2Vec 2 and the brain and end up with a correlation score that tells us how good this mapping is. You can see that on average it's extremely low, and because we're trying to predict at the individual time sample for every individual electrode, so it's extremely low. But it's nevertheless consistent across subject that you can find a mapping with a trained model. And this mapping is improved when you focus on the deeper layers as opposed to the early layers. All right, so the summary, this bar diagram is actually a summary of this plot. So when you try to predict brain activity with a random layer model that does not mean trained, you can already predict some part of brain activity. But you get an improvement in many brain regions if you do train Wave2Vec 2. And you also observe that you have another gain of brain prediction if you now focus on deeper layers in the model. We can sort of quantify the gain of training the algorithm on natural speech and the gain of the hierarchy by focusing on different layers. And that's a similar phenomenon, but this time with the analysis over time. Now, Wave2Vec 2 is a speech model, so it's unsupervised, but the input is an audio waveform, and this is not trainable at the same scale as large language models today, because speech waveforms are actually pretty heavy material. So what the industry has really focused on in the past couple of years is text-based models, like whatever, ChatGPT, and in the case of OpenAI, and at Meta, Llama models. And these are models typically trained to predict the next token or the next word given the preceding context. And they can be trained at a much larger scale because they are trained on text material, which is much more lightweight. when we apply the same analysis on these text-based models, we observe something relatively similar, except that the hierarchy effect is not at all as clear. And that presumably comes from the fact that the first layer of a text model is already at the word level, right? It's already presumably capturing some sort of lexical semantics. So it doesn't have access, of course, to the phonemes and to the mouth spectrogram, or because it's input directly with text. Okay, but nevertheless, when we focus on this, we observe something similar to what we had observed with the linguistic features. The early or low-level speech features tend to be represented similarly across age groups, and the let's say higher-level features that are typically represented in text-based models tend to be observed but more or decodable better from the older participants. And this is all the more true that the models get trained over a large amount of text. All right. So the summary of this study is the following. These pediatric recordings during natural speech comprehension provide really an unprecedented window over the development of language processing. And what we observe is two things, right? Is focusing on linguistic features on the one hand and linguistics on AI features on the other hand. With linguistics, we can confirm that there is already a rich hierarchy of language features that is present in the child brain. And we observe that within this hierarchy, it's the lexical representation that appear to continue to develop across ages, which resonates with what we know about language acquisition, because a lot of this is a lot of language or speech processing is actually acquired before 2-year-old, especially for the low-level features. And these changes seem to be predominantly observed in high-level regions like the infrafrontal cortex and the anterior temporal lobe. With AI features, we don't, in a sense, learn much more than this first observation. But for the first time, we have models that are trainable. So they're not just description of language, but they also model that acquire these descriptions by exposition. And so for the first time, we can try to compare the developmental trajectory of humans on the one hand and models on the other hand, to try to see how they may capture similar representations during their training. Now, this is a study with quite a lot of limitations. I'll just mention 4. This is on French participants only. The youngest patients are 2-year-old, and we know that language acquisition starts way before 2-year-old. Actually, it probably starts even before birth. And this is really a technical hard limit that we cannot go over at the moment. Another big limitation is that we are here focusing on language development in patients who suffer from pretty intense epileptic seizures, and that presumably, or at least on average, it does affect language development. So it's not impossible that what we observe here is not necessarily completely representative of what you would observe in a healthy cohort. And finally, the analysis with the AI models allow us to have first models of development of language, but the representation that they acquire remain relatively opaque, like any of these AI systems. Okay.
So Jean-Remi,
Yep.
is the limitation of not using MEG is the voxel resolution? Not voxel, but electrode. I mean, if you do all of this with MEG, can you get even close to this?
I don't think you would get the same spatial resolution with MEG systems as to intracranial recordings. I think there are a few benefits, but one of the main benefits of focusing on intracranial recording is that it's heavily immune to movement noise, as long as they don't move around the cables on the head. And that's very useful for these children, because it's very hard for children to remain still for a long period of time. And so having them stay during a full week allows us to have multiple sessions, multiple chapters that they listen to without the kind of noise that you would get with MEG. So within a given subject, you basically end up with much more data than what you would have in MEG. That would be my the main benefit.
Presumably younger adults and and stuff, at least as far as this problem.
Absolutely. If you focus on, let's say, 7 and above, you would be able to extend this kind of research to teenagers and to adults. And I mean, in adults, of course, we do this as you know, but focusing on the moments where language is developing the fastest is probably I would say this would be the priority.
Mm.
So there is not much development of language, let's say after 12, right? You still increase your vocabulary and your reasoning abilities, of course, are changing. But in terms of, let's say, grammar, for instance, there is no obvious changes during after that time period. Okay, I'm gonna have to make choices on what I should present. Oh, I'm gonna switch gear entirely and yeah, go ahead.
Hold on, moving on, so back. Before we move on. Hi, Jean-Remi, it's Ronnie here.
Hey.
It's great to hear from you. I can't see your face, that's the only inspiration. You are covering a wide range of ages from, what do you say, from 2 to 12? So here comes the question. So when we talk about the models and stimuli, they're two separate but related problems. So, you know, it's the same story that it's the same story of learning to all of these children, right? I mean, the story when you talk to a child is going to be tuned to a particular age. Like you don't talk to a 2-year-old the same way you talk to a 12-year-old, right? Was that
right?
That's the first question. The second question is about the models. You know, these are models that are, you know, taking all the data in consideration. Are you considering training models with what you would imagine would be the amount for different ages and see if you can simulate learning?
Yeah, absolutely. Two great points. So the first one I think relates to one of the comments that was raised earlier, which is indeed, I think for any, this is true for any stimulus, but it is particularly true for language. The depth of interpretation depends on your cognitive ability. So when you hear The Little Prince, in this case, they listen to this book. When you hear The Little Prince as a child, you don't understand or hear the same thing as an adult would do. Like you focus on elements that adults would probably discard, and on vice versa, the adults would see a narrative structure that the child would not see. And so I think a typical effect would be that at the end of the story, the adults do understand that, well, a good hypothesis is that the Little Prince dies at the end, whereas the kid would not understand that. And so like the emotional content is completely changed depending on the depth of interpretation. And we don't resolve this, of course, but I think this is really a means to get there, is to say, okay, it's very hard for these young children to perform classic cognitive tasks because the attention fall off, because they don't want to participate. And these natural stories provide a window into this, but I agree that it's not fully conclusive for these deep questions of what do they actually understand within each of these sentences. But hopefully we can have elements that highlights how this may be. And on the second question, I think this is precisely the right track, and one of the focus in the team is to not just rely on these large language models trained at scale on trillions of words, but to try to systematically change the amount of data that they are trained with, to see what kind of amounts suffice for these models to be similar to the brain. The preliminary results that we have so far is that you don't need to do the full training, but certainly it's still many more words than anyone would ever hear in their lifetime. So there's still a huge efficiency gap between the models and the brain.
Couple more questions, go ahead.
Yeah, sorry, I'm gonna delay the next, I'm sure it's been hard to talk, but I didn't want myself. So hopefully I'm not being a dead horse, but just to return to the topic of self-supervision, I totally agree with you. I think like self-supervised model is the way to go. And I think these are very compelling results using this sort of model. trained strictly from speech signals independently from neural data. I think my question, I'd like to introduce the topic of fine-tuning, because these self-supervised models are, of course, kind of like multiple representations of kind of everything that happens in speech. I think it would be very exciting. You have the opportunity here to disentangle the different kinds of speech tasks that the brain does. So you can imagine a case where you would have a matched model architecture to make all of those comparisons now. So you can imagine a case where you fine-tune wave detect for pseudo recognition, or source separation, or ASR, and then rerunning your analysis. And I'm very, very interested to see how those align or call out different regions of cortex that we've been trying to uncover to do these different kinds of tasks.
Right. These are, I mean, beautiful suggestions. We have not done this for this study with children, but we did a bit of this in the past with fMRI and MEG data. So for instance, what we had tried is to train different versions of Wave2Vec2 with the same amount of speech, but some of them in Mandarin, some of them in English, some of them in French. And then we compared, depending on the training, whether they would end up with similar representations to the French, Mandarin, and English speakers, to try to isolate what is specific. We also try to see what type of language abilities would be, let's say, a predictor of for a model to be more or less brain-like. And I mean, we have many different things that are sort of significant, but it's not like we have one clear-cut effect where we can say, okay, if the model can do this, then it's for sure going to be similar to the brain. It tends to be multifactorial, at least for now, up to what we've been able to identify. But we haven't done this for the intracranial study here.
Jay, we have about 10 more minutes left, so I'm going to let you continue, and we'll take questions at the end. Okay. Unless you want to do more questions.
No. Well, I'm happy to take more questions, but I want to see what would be the most exciting for this cohort. I think I'll focus on typing. I know that tomorrow it's BCI, but might as well. So this hierarchy of representation that we study in the case of speech comprehension is typically sort of bottom-up hierarchy, right? You have the auditory cortex that presumably represent these low-level acoustic features, and increasingly in the speech network, you get representations of phonemes, morpheme, words, syntax, and semantic composition. And it's often much harder to study the reverse effect for a simple reason, which is in non-invasive neuroimaging techniques, it creates a lot of artifacts, and even in intracranial recordings, because of the audio sound that are being generated when we speak, for instance. So what we thought of doing, and this is work in collaboration with Svetlana Pine at BCBL in Spain, and that was led by Lucy Zhang, who is wonderful PhD student that we have in the team at the moment. What we thought of doing is focusing on a different modality of language production, which is typing. And I'll show you. I won't show you each of these 3 points that I highlighted here, because this would take me too much time, but I'll focus on the first one, which is that we can track a top-down hierarchy of representations thanks to energy. All right, so the setup is pretty simple. Participants are in the MEG, and they read one sentence at a time in a so-called rapid serial visual presentation, so that each word is presented one after the other. This is an experiment in Spanish because it happened in Spain. And after some time, there is a cue that tell them, okay, now you have to type this sentence on the keyboard. And the advantage, of course, is that unlike speech, which activate the motor activity very close to the MEG sensors, the keyboard is far away from the sensors, and therefore does not create the same type of artifact. They don't have any visual feedback on when they type, which is also another advantage, because unlike speech, they don't have this sort of sensory information which is confounded with the motor information for data analysis. Right. So we apply the same type of linear encoding and decoding technique that I showed you before, and we can time lock MEG activity to the onset of each typed word. And so T0 here is the onset of the word as it is being typed. And so this is actually the decoding of the first letter of the word in blue. But we can also try to do the same thing for different features of language. For instance, the first syllable of the word, the morpheme, the word itself, the lemma, and the context. For each of those, from syllable to context, is actually an AI embedding of the syllable, morpheme, words, and context. So you feed into a character level language model longer and longer amount of letters to reach the level of syllable, word, or to have the full context. So we can track all of these significantly above chance, but what is interesting is to normalize this by the maximum decoding scores, because we are working in different sort of spaces. And when you do collapse all of these curves into a normalized decoding score, you end up with this diagram here, where again on the horizontal axis is time locked to the onset of word production. And what do we see? We see that just before word production, we can decode the first letter. But if we come back a little bit earlier, we can start to decode the syllable, and then even before this, the word, and even before that, the context of the phrase. And that, to me, is striking, because that means that we can track with this MEG approach the top-down hierarchy of representation. The brain first starts to represent the context, then starts to represent the word, then starts to represent the syllable, then the letter, and finally behavior happens, and the execution is being initiated. We can try to understand more in detail how this is actually represented in the brain by trying to see whether inside of these decoders, whether there is a sustained activity patterns. For instance, you would, let's say, decode the button being pressed, the letter being pressed on the keyboard. If it sustains, there is an analysis which is called temporal generalization analysis, which ends up being a square matrix. Whereas if your activity that codes for the letter varies over time in the brain, you end up with a diagonal temporal generalization matrix. I'm being very elusive here because of the sake of time, but if you're interested, I'm happy to give you reference to understand why that is. And what we observe overall is that the decoding of individual letters, time locked to the word onset, they end up with a very sharply diagonal pattern that indicates that the representations of letter is actually changing over time in the brain. So for instance, if we focus on 3 projection of brain activity and look at this at, I should say, let's focus on one time sample. So if we look at only one time sample, which is at the beginning of a letter onset, what this dynamic activity patterns allows you to do is to represent multiple words at the same time. This is what we see in this diagram below, where we have each axis is one linear decoder, either a decoder trained at -100 milliseconds with regard to word onset, at word onset, so 0 milliseconds, or 100 milliseconds after word onset. So we have 3 decoders, 3 linear projection of brain activity, and each dot here is the decoding of the letter. And what you see that you have each of those moving in this 3D, but in fact in a high dimensional space, and that tells you that the code is constantly moving in the brain, and this constant movement allows you to represent multiple letters at the same time. So if you focus on just one time sample, you can decode the current letter, the preceding letter, the one before this, and so forth. This is just an animation of the actual data, and time indicates the time relative to the word onset, and we can try to decode different letters depending on different linear projection of the brain data. Now, this dynamic coding scheme is something that we observe at the level of letters, but it's in fact happening at every individual levels that I indicated you before. So syllable, word, oops, there is a typo here, context. And each of those gives you a different temporal generalization matrix, but all of them are diagonal, but with different width. So they actually move at different speed in brain activity. The higher level representations tend to move in the space of brain activity more slowly than the lower levels. And that tells us a little bit how the brain articulates language. So at every moment of time, you have a representation not only of each of the different levels of the hierarchy, but also of what happened beforehand and what will happen next. And at the letter level, when you type, what happened next is going very quickly. But at the contextual level, at the word level, things are moving more slowly, and we can capture this from brain activity. Right. So I'll just stop here, given the sake of time, just to give you a sense of how we can use these AI models to not just be amazed by their ability, but really to try to use them as tools to understand how the brain may represent information. Because in both the case of speech comprehension, but also in the case of typing, these AI models allows us to have new hypotheses about the vectorial space or the patterns of neural activity, which represents phonemes, letters, movements, syllable, words, and they give us basically a hypothesis to test and see whether the brain indeed represents information in the similar way. I'll skip all this to get to the end. You missed all of these great theories. I want to emphasize just one thing before I close on this, is that there is still, and this has been discussed slightly in the question, there's still this major challenge, which is, I think, both for AI and for neuroscience, which is that the comparison of these AI models to the brain is fascinating, of course, but it should not hide the fact that these AI models are trained with a ridiculous amount of data. And so that's, to me, really legitimizing our whole research to try to understand the exact learning principle, the exact neural architectures that allows us to acquire an ability like language so efficiently. And this is a non-trivial problem, of course, because we know that non-human animal species have certainly a very hard time to acquire the same ability, even after the same amount of exposure as us. With this, I'd like to highlight again that this is some work of the wonderful team I had the chance to work with, and I'm happy to take more questions if you have any.
Thank you.
Hey, thank you so much. My name is Ken Grant. That was really wonderful. I want to get back to the question that Giovanni asked, because in adult-child interactions, we don't speak the same way, right? And so I think by feeding an adult read book to a child to learn how a child is acquiring language may be an issue. I'm just curious if you might have a different result. Who knows? If, for example, you talking to a 2-year-old, often has this adult-child interaction where intonation is exaggerated and so forth. So I'm wondering that might have a different hierarchy of for me, that automatically is the prosodic stuff coming early, very early. That's what the parent is trying. That's what the adult is trying to communicate to the child. Not meaning, not words, but patterns, intonation, and so forth. So anyway, I'm just wondering if you would have switched the input to be relevant to the way people actually talk to each other. Right? Maybe that, I don't know what that would have done, but just a question. If I understood what you were asking, yes, maybe that would have been it. Okay.
Yes, I think this would be a great experiment to do. We are moving in slightly in this direction. We're trying to have language production paradigms where we engage in natural conversation with these patients. I mean, everything is difficult, of course, because when you go in this direction, then things are less controlled. Like it's not just the brain which reacts differently, is that the stimuli themselves differ across ages because they don't tend to have the same conversations. But yes, I think that would be wonderful to be able to decipher this with stimuli that are more adapted to each age group. The comparison would become to some extent harder, but it could still be enlightening.
Simon Ling from the University of Maryland. So Yeah, we know that like for both humans and for these like waves to that, for example, like the underlying task structure is start with this input, or output, and do something that is basically linguistic. And so to some degree, like it's made into the structure of the task that you need to employ these hierarchical representations. So for both black boxes, and even if you would come up with a third sort of way of doing this, like no matter what black box you use, basically, you kind of, to some degree, like have to come up with these hierarchical representations that start at the level of sound and somehow take you to the level of like meaning. And so I guess to what extent are you saying, like are these results simply like just reflecting the structure of the best? Like you're showing that lower levels of the model are like picking up like phonics, stuff like that, and higher levels are meaning level. Like to some degree that has to be true, right? Like it can't be otherwise. And I guess like my question is that simply what we're saying, or simply reflecting the structure of the task by like showing these map each other? And if not, if we're saying something more about the transformations that happen from lower levels to the higher levels, is there some baseline that's appropriate that we can compare to? That's kind of like what would be a null baseline, I guess? If we're saying something more than the structure involves hierarchy.
Okay, so let me try to answer the first part. So I think I agree with you that it could not have been otherwise, but I agree with you kind of after the fact, because if I recall correctly, a bit more than 10 years ago, when I was writing grants on even trying to suggest the idea of comparing machine learning models trained on speech to the brain, the classic response was that that was just dumb, because of course they would not react like the brain. They're not designed. They're so biologically implausible in so many ways, and that's still true to some extent. But it's true that the more we do this comparison, and now we do this, I mean, at scale, we have more than 1,000 participants recorded with MEG, fMRI, and intracranial recordings, and we do this comparison across pretty much all language models that are publicly available, and we find the similarities to be heavily consistent. So that seems to be a necessity for these models to represent language to some extent in a way which is similar to ours. But I don't think this was necessarily expected. But still trying to understand why that would be a necessity. I think this is where theorists are absolutely needed. Like we need to understand what sort of mathematical principles require a vectoral system to represent a language in this way, because you can, I mean, if you're sort of you can come up with counterexample that are handcrafted that would have the same language abilities but not represent language in the same way. So for instance, if you encrypt a deep net, you can have the exact same capacity, but the representations is completely shuffled and indescribable. So of course, this is not what we observed with classic deep nets, and the reason why they tend to converge to similar representations, I think, remains to be theorized. Yeah, that's where the need is.
I guess it's a very good. So if you were to like encrypt, I think whatever a particular representation, encrypt it, that would actually be interesting next time. Could you then learn a linear mapping from the encrypted version of the vector to the neural representation? And if you can't, that would be an interesting goal, right? Just want to say it as a comment.
Sorry, you cut out a bit. So, what is your comment on the encrypted version?
So, as a null baseline, taking the vector representation, the internal representations of like wave2net, for example, or any of these mechanisms, encrypting them, and then showing that if they were encrypted and they weren't actually original representation, you cannot
keep this for now.
The same.
Can you connect on Zoom?
Performance would be very, very bad.
I'm sorry, there are other people who are speaking at the same time, so I didn't hear the question. Sorry.
So I was just thinking about like a null version of the like once you train the black box model, you want to sort of test that against a null background, and I'm guessing the null baseline would be something like your just a moment. I hope you heard this time.
Yep. Yeah, I mean, just very, that will be a loose answer, but I think this work has not been done thoroughly. So yeah, more baseline are necessary. But I'm just going to reiterate, which is that even if that seems trivial now, the principle that leads a neural network to converge to similar representation, irrespective of the training type, the architecture, I think this is something which is not understood. The underlying principle that drives this convergence are not understood, and this is where we need theorists. Yeah.
Thank you. Jean-Remi, this is
Yes.
Just a comment on what you said about the enormous mismatch between the amount of stimulus that is the child is exposed to and the network model is exposed to. There is a big difference in the sense that the child is also exposed to the environment, feedback from the environment. He gets hungry, gets input from his mom, their emotions and stuff like that. That are completely absent from the training of the model. It might get the information, but to get the same information, it's going to interpret a much larger corpus, make sense of these environmental constraints.
Yep.
I'm wondering whether there's some way of getting a handle on
No, I mean, absolutely. I agree. Like, this is the comparison here between AI and the brain, and the highlight of the difference is really just focus